Well, welcome everyone. I am JJ. Let's come in and work an example problem. So in this one, we're saying let's use the area method to draw out our shear moment diagrams. So rather than coming up with an equation every interval, we can directly apply just a handful of rules. And we work from left to right across our beam and just work through everything. So we know if we have a force that acts up, our shear diagram immediately goes up. If our force acts down, our shear diagram immediately goes down. That force will cause no immediate change in our moment diagram. So we just keep going with other rules there. A counterclockwise couple moment would make our moment diagram immediately decrease. Clockwise would make it immediately go up and do nothing to our shear diagram. For our distributed loads, if I'm looking for my shear at the end of a distributed load, it's just the shear at the beginning minus whatever the area of that distributed load was. And then in our moments, it's going to tie in with this, but our moment at the end of an interval will be our moment at the start, plus whatever the area of the shear is. So we'll break everything up into areas and just work left to right. So if we're coming in and doing that, we have a beam. I already gave our support reactions on here just to move everything along. We want to come in and say, well, where does our loading change? Let's make an area out from that. So I have one distributed load here. I can just come in and say, let's call this area 1. Area 1. So our work, I just want to find that area. Area 1 is a rectangle. So it should be the area of a rectangle is base times height. Our base is 6 meters. The height of our distributed load is 20. 6 times 20 gets us 120 kilonewton meters coming out for that. Not kilonewton meters, just kilonewtons coming out for this. So we can work then. We can go left to right across this. So we'll always start both the shear and moment diagrams at 0. So we start here at 0. And as I start to move to the left, two things happen here. I have our concentrated 80 kilonewton force and a distributed load starting. Always resolve that concentrated thing first, that thing that happens in infinitely small distance. So immediately, we're going to go up. So it's right on our axis. We're coming up here. And we can label this point. We're up at 80. And then we know over that next interval, our shear should decrease because our distributed load goes down. So our shear at the end of this, let's call that point B. Our shear at point B, VB, should be equal to our shear at the start here at point A. And we'll always use the last point that we plotted in here. So we'll use the 80 equals 80 minus our distributed load from A to B. Well, that's just area 1. Area 1 is 120. So minus 120. This should get us to negative 40 kilonewtons. So we're going to start here at 80. I'm going to drop down and end up here at negative 40. Negative 40. If our moment is the integral of shear, shear is the integral realistically of load. If I have a constant here for my load, if I integrate that, I'm going to get a linear function. So I can get a linear decrease from 80 down to 40. There'll be one more point I need to find right here where my shear is 0. That's going to correlate to a max or a min point in my moment diagram. But that's my first interval in my shear diagram. Let's go ahead and shade that in. Then we can keep going with this. So what's our next interval going to do? Well, if I look up above from B to C, there's no distributed load. If I integrate 0, I get a constant out. So I get a constant all the way until the right edge. And then we come back up to 0. We're at negative 40 and that entire range in there. And that's my entire shear diagram. Negative 40. Let's move that so it's off the line. We'll just show it for the entire base here. Negative 40. This point right here, we're going to want to find, because that'll be a local max or a min point up above. So let's call that, we'll come from the left edge in here and go out here. We know this entire width here is 6 meters, and I want just what's measuring to that 0 shear point. Anytime that we slope across the x-axis, we gradually change. We should find that. So what's our distance to here? I'll call that x1 from A to my 0 shear, x2 from my 0 shear to point B. And I can use proportional triangles to find that. The slope of this line is constant, so I can say my rise over my run is also going to be proportional in there. The numbers will go in the same, but the actual values coming out are going to be the same. The ratio of rise to run is the same. So really in this triangle, my base is x1, my height is 80. x1 over 80. Should give me the same thing as x2 over, well, my height is, technically it's negative 40. We'll put that as positive. x2 over 40, which is going to be my total change in distance here. My x was 6 equals 6 divided by my total change in height from 8 to negative 40. Well, that's just my area. That's 120. And I can use that to solve for x1 and x2. x1 over 80 equals 6 over 120. x1 is 4 meters. x2 over 40 equals 6 over 120. x2 is 2 meters. If we check that, 4 plus 2 does get us to the total base of 6. That's my next step in there. With that known, I can come in and start finding additional areas. So I already found an area 1. I have a triangle here. We're going to call this area 2. I have another triangle. I'll call area 3. And a rectangle, area 4. So I'll have 3 more areas I need to calculate out to make my moment diagram. So let's come in and tackle those. My area 2 is a triangle. Area 2 should be, well, the area of a triangle is 1/2 base times height. The base of this triangle is x1, so 4 times the height is 80. 1/2 of 4 times 80 is going to get us 160 kilonewton meters. My next area is area 3. Area 3 is, again, a triangle. 1/2, my base is x2, so 2 meters. And my height is negative 40 at that point. Negative 40. I'm getting a negative area here, which makes sense. I have a negative shear, so my area is negative then. This is going to get me negative 40 kilonewton meters. And then my last area, area 4. Area 4 should be base times height. It's a rectangle. My base is 3. My height is negative 40. 3 times negative 40 is negative 120 kilonewton meters. So let's plot this one out. We're going to start at 0. The only thing that causes my moment diagram to immediately change would be if we have a couple moment. There's no couple moment applied on this, so we don't get that instant change in here. But we can say, so that our moment at the end of the area right above it should be the moment at the end right here is our moment at the beginning, 0, plus area 2. And area 2 is 160. So we're going to increase up here to 160. Our shape of that, if I integrate my shear, I get a moment function coming out. The integral of a linear line should be a quadratic line. If I was sloping down here, my quadratic should be concave down. So we'll plot just a general looking parabola. Then we can keep going with that. My next area goes from the point we just plotted to point B in here. So my moment at point B, the end of area 3, is the moment at the beginning, moment at the start, 160, plus the area of a shear. 160 plus a negative 40 would get me here to positive 120, 160 minus 40. And it still is a linear function. We're just continuing the parabola on. Then we have one last area. The moment at the end of my area, at the end of area 4, is the moment at the start of the area, 120, plus the area of the shear, area 4. So 120 plus a negative 120 is going to bring us back down here to 0. We had a constant for our shear, so we should get a linear function for our moment. And that's it for us. We can shade that in, and we're done with our problem. A lot quicker than coming in and trying to find equations for everything. There's value. Sometimes we need that equation to be able to go on and do more in-depth stuff down the road. Sometimes we need it just in one interval, and it might be easiest just to do it once and then still make the rest of the diagram. But if all we're doing is making shear moment diagrams, a lot of times this is by far the easiest approach for us. But hopefully this is a useful video. If it was, stick around, watch more videos. Let's get you in A with JJ.